My second talk here at Devoxx Ukraine. I know that there is Bersater speaking in the next room, so I'm happy really to see so many people here. Yesterday we talked about GraalVM, how you can write polyglot applications with GraalVM, what is the current compatibility level, and how does various frameworks support GraalVM. So today we'll talk a bit more about performance, like what is achievable with GraalVM if you want to optimize your application's performance. And we'll also talk a bit more about GraalVM native image, which is GraalVM ahead of time compilation mode. So let's begin. So the performance itself is sometimes even hard to define, leave alone measure. So for example, if you would want to define and measure performance of your application, what would you typically measure? Like just shout out versions. Throughput, okay, that's a good one. What else? Latency, another popular one. Any more guesses? Memory usage. Very good. So if we check, for example, the optimizing Java book, this is the few metrics that it offers for consideration. So throughput, latency, those are pretty straightforward and self-explanatory ones. These are the ones that you mentioned. A few more are like this. So for example, capacity, how much work at the same time can your system or subsystem measure, like simultaneously? Another one is utilization, whether or not your system is capable of making the most out of resources, specifically the CPU, or is CPU just handling the OS tasks and some basic housekeeping tasks. One more is efficiency. So if you have a cluster of servers and, for example, you add twice as much, does your system, let's say, throughput scale by 2x too? So typically that's an ideal case, and that is not something that you will see in real world, because in real world other factors will interfere and you may experience this like perfect linear scaling for quite some time, but then you will see some downfalls on that. One more is also scalability, like how well does your system scale if you add more resources. And the last one is degradation. So if you increase the load on your system, either by increasing the number of requests or the time at which those requests arrive, how does your system handle that additional load? For the purpose of this talk, I suggest that we focus on the following ones. This is throughput, efficiency, and scalability. And we will talk specifically about how we can optimize for those with GraalVM. So I see quite a few new faces comparing to tomorrow, so I will basically very quickly introduce GraalVM so that we have some common language and understanding of basic concepts. So GraalVM is a universal virtual machine, and it has this mission of running programs more efficiently and also making developers more productive with new capabilities, new tools, and more convenient development process. And the way this is achieved is by those goals. So the first one is providing high performance for abstractions of any language. And all three parts of the sentence are important because sometimes people consider abstraction being a trade-off with performance. Meaning if you write good code, quite abstract, following best practices, that would mean downfalls in performance. Or if you want your code to be really high performant, then sometimes people say that you would need to write it in a quite different manner. We think that this is something that your underlying system, like a virtual machine, should be capable of handling for you while you can focus on your actual tasks. One more goal that we have is providing low footprint and fast startup mode for Java applications by compiling them ahead of time into native executables. Another one is convenient language interop. So GraalVM provides a few language implementations, and you can add even more to it if you, for example, have your own custom in-house language, and they work really fast together because they are all implemented on the same platform against the same rules. And the last one is simple embeddability. So GraalVM is quite easy to embed in various environments and get access to the languages and capabilities that GraalVM offers. Yeah, so that is the basic overview of GraalVM. So today we'll be talking mostly about Java and JVM languages, but that's not all that GraalVM can offer. Also, GraalVM has a JavaScript engine, which is called GraalJS. We have Ruby implementation, so you can run your applications written in Ruby on GraalVM. If you're doing data science, perhaps you must be interested in R. And also, we have quite an early stage, but interesting implementation of Python. And the last thing here is C, C++, basically any language that you can compile down to native code, to LLVM bitcode, you can also run on GraalVM. Talking about platforms, GraalVM can be used in the context of OpenJDK. Also, it can run Node.js application, and you don't need to do any compatibility effort to make them compatible with GraalVM. They will be ready to use, ready to be run just the way they are. One more interesting use case is in database. For example, you can get access to more languages and more language ecosystems in your database if you want to, let's say, use some JavaScript to validate data in your database. And the last one is the actual mode that we'll be talking quite a bit about today, is a standalone where you can compile your application into a binary that will no longer be dependent on the JVM, meaning that you can run it just the way it is. GraalVM comes in two versions. The first one is Community Edition. It is open source, free to use. Development is happening on GitHub. You can take a look at it. You can contribute, see what it looks like inside. And also, since it's written in Java itself, it will be fairly easy for you to understand the way it's written. The other one is Enterprise Edition that would require a commercial license to use in production, but it's also free for evaluation purposes. So for Java, that is the important distinction I would like you to memorize from this talk, because GraalVM can run your Java JVM applications in two big equal modes, which is just-in-time and ahead-of-time compilation mode. Because the ahead-of-time compilation mode itself is so exciting, sometimes people associate GraalVM only with the IoT mode, like GraalVM is native images. That's true, but it's not the whole truth. So you can run it as your normal Java application too. The way to do it is just to replace your Java distribution with GraalVM, and then you can run your Java application using our Java command and just give it your application. So with IoT mode, things are slightly different. So you can think of working with your application into two steps. So first you build your application image, and then you run it. And the idea why we need those two steps is to move all the heavy lifting from the runtime to build time. So at the build time, you perform analysis, you perform optimization, and you compile all of that, so that in the end, at the image runtime, it can start really fast, and it will only need a fraction of memory compared to a just-in-time compilation mode. So this is a basic overview of a Java dynamic execution model, and I think that is something that you are really well familiar with, but we will just go through it so that we can compare it with IoT. So the way it works in a nutshell, that your class loader will load your classes, and they will be first executed in interpreted mode. And the reason why this is needed is because compilation takes quite some time, and also there is data needed to make decisions about compilation. So first it runs in interpreted mode, and then along the way it kind of gathers the information, the profiling data about your application behavior. Then it starts compiling, and one more interesting concept about dynamic execution is the concept of de-optimization, and what it means is a JIT system like Hotspot VM or GraalVM JIT can perform this optimistic assumption about your code behavior and compile according to those assumptions. And if at some point those assumptions become no longer valid, it can de-optimize, go all the way back to interpreted mode, and start running again, and maybe compile again if there is a need for that. So for native image generation, the process is very different. So we start as an input with your application data, with your libraries, the JDK classes that you are using, and also what we get inside is Substrate VM, which is a small, slim implementation of virtual machine that we pack inside this binary so that you can get the actual features you would expect from a managed environment. And we start points to analysis of this whole thing, and we run it starting from the entry point of your application, trying to find all the reachable code ahead of time. What we also do along this time is we run initializers. So we initialize your code along with performing this point-to analysis, and this is like an iterative process. So we do it over and over time until the fixed point is reached, and we know that every code is found, and we can compile the application because we already have all the information. So when we compile it, in the end, we have a native binary or share library, and it contains two parts. This is your actual code in text section and image heap, so pre-initialized image heap so that you can start really fast with your application. And if we compare those side by side and see what is happening at the image startup time, at the application startup time, you see that it's quite a difference. Yeah? So if we compare those two systems, they're quite different in terms of what's happening, because on the left, you see that there is a lot of work going by this code loading, code optimization, code compilation system. So first you load, when you start your Java process, first you load your GraalVM executable itself, you start verifying the code, then you start interpreting, you gather the profiling information, you compile it once, you compile it twice. There is quite a lot of work to do when you do your application in a just-in-time compilation mode. When you're running it in a ahead-of-time compilation mode, things are slightly different, so you just need to load executable itself, and you can immediately start with precompiled code. If we compare the memory footprint, situation is kind of similar. So in terms of memory footprint, what do you need for just-in-time system? You would need, once again, your GraalVM executable, you need the application data, reflection metadata, the compilation infrastructure itself, and when we are talking about compiled binary, that's only the application itself and its data. Now, what about throughput? That's the first performance metric you mentioned, and that is something we all care about. So JIT systems are very good at throughput because they have this profiling information available at runtime, and they can observe your application behavior at runtime and optimize specifically to the way your application behaves. And that is something that is very hard to beat unless you know this information. So with IoT, when we build this native image ahead of time, we need to handle all of the possible cases, because ahead of time there is no way to know exactly what will happen. But we also do, we provide this more predictable performance. So if predictability is important for you, if you want to understand and optimize specifically for a certain level of performance, that will be fairly good at the beginning and it will stay more or less stable over the time, then this predictable performance would be helpful for you. There is one more thing that we will go through in detail later, and that is profile-guided optimizations. So you can gather this profiling information and give it to us at the image build time, so we can build the application and optimize for the specific use cases that you provided us information about. So that is something that definitely helps to make better optimization decisions at the image build time. And if we compare some metrics for the both modes and select the following ones, like P throughput, reduced max latency, packaging size, startup speed, and memory footprint, then those two will compare like this. So for JIT systems, as we already discussed, you will get great peak throughput, and also you will have a lot of ways to optimize for reduced max latency, because with all that information available, that is something very helpful for JIT systems. For IoT, the ratio will be like this. So you will get fast startup because there isn't that much work to do at the image runtime, because you already done that at build time. Memory footprint also will be smaller because the only thing we are bringing into memory is the compiled executable, and we are not bringing all that infrastructure to load and optimize code. So currently they compare like this. And let's do the demo and see how both of those will affect our application performance in both modes. Okay, so what I have here is a micronode, like you know, Microservice Framework for Java. And this is a sample application that is doing basically like a simple web service. So you send requests to it, and it will respond to you with a random conference name. So if I wanted to show you what it does, I can go like this. I just basically do Java, jar, and give it my application. And it will be running in a just-in-time compile mode. So if I check the result, yeah, it was the old one. Yeah, so basically what it does, it responds to me with those random names. So let me shut it down so we can do it in an AOT mode, and I'll just to make sure that, yeah, it's down. So I already have it precompiled as a native image, and the way to run it will be like this. So I just run it as already precompiled, and you see that immediate startup is so much faster, you can barely notice it. And if I check whether it does the same thing, yeah, it does. It's once again those random conference names. So that's the startup time. What if I wanted to go one level deeper and understand how does it perform in terms of consuming CPU? So for that, I have a script over here that will measure the CPU time needed not only to start, but to successfully serve the first request for me. So if I apply this script to my application in a just-in-time compile mode, I will see those numbers of CPU usage. Okay, so it started the application. It was started in 1.2 seconds. I don't know, maybe I will put it a bit upper so people in the back can see it too. And the CPU time consumed to actually do the work, handle the very first request, respond to it, is 3.1 seconds. Now, if I do the same to the compiled image and compare, I expect to see a different number. Let's try. Yeah. So this time, the CPU time used is 30 milliseconds. That's once again because we don't need to do all of that work at the very beginning. And that's a fairly simple web service, so you would kind of expect that it doesn't need to do all of that heavy lifting when you just start it. There is also a way to look even more into it. So if I wanted to measure the memory usage and also, once again, the CPU usage in both modes, but kind of have a better overview of it, I can do this. So I will send a few requests to this server, and I will use PS record to output this information for me in the form of plot. So to do this, I will apply this plot script. So it is sending those couple requests, and now it will build for me a plot sharing details about it. Yeah, that's the current time. So if I look at it, it looks like this. So the way to read is, well, first of all, this is kind of zoomed out. You see how big the numbers are. So even those spikes later on, they may seem like they are smaller, but in fact, that's quite a lot because if you look at the scale, it's quite huge. And what is happening, all those spikes in the very beginning, is a lot of CPU time used when you start your system in a just-in-time compilation mode, because there are all those important operations and spacing operations to make your application running. And when we take a look, for example, at memory used, it's a bit about 350 megabytes. So I will run it once again on my precompiled image. I will just rename this one so it's not overwritten. So this would be my plot JIT. So we are getting those names back, and we have one more plot. So let me just open both of them so we can compare side by side. So they may look somewhat different. I just want you to understand that the scale is different, right? So this one on the left is kind of zoomed out. But what you can already see is in the second case, in the case of a compiled native image, there is so much less work going on because the system is only working when we are actually getting those requests and serving those requests. And that's basically the way how a typical service like this should look like, because there shouldn't be all this heavy lifting happen in the very beginning. You just receive a request, serve it, and you are done. And you don't need to do all that much work. And also, if you take a look at the memory used, in this case, it's about 20 megabytes. Excuse me? On second graph, GrowVM, like, there isn't much like a difference you see, because here it's a huge difference, and here just because the scale is zoomed in, it may look like it. It can be like different time, but on average, it's more or less the same. There is still some work going on, like we do serve those requests, but anyway, there is like a small implementation of VM inside, so there are still some tasks going in parallel with serving those requests. So what about load? Because when we talk about performance, load is perhaps the first thing that comes to our mind. Like when we apply load to our system, how does it handle it? How does it behave under it? So for that, I will apply load to both of my applications in a form like this. So I will send 10,000 requests in 10 iterations, and will measure a couple of numbers for each of those. So if I apply load to my just-in-time compile application, so it started running, but it will take quite some time to serve those requests because it's 10 iterations and there is a bunch of requests in each of them. So that's a just-in-time compilation mode. So you see that it's warming up over time, and let's wait for the final results. So the numbers we see here are CPU milliseconds used, requests per CPU seconds, RSS size, and the last one is kind of efficiency ratio, meaning we take requests and then divide them by the amount of resources we needed to serve those. So let's run it on a native image and see how it will work under it. So you see that even like the first iteration results appeared faster. And if you look at the last column, mostly presenting efficiency, you see that we are able to serve requests with less memory. There is also something else that we can do with it. So you see that in this case, the RSS size is 280, but in fact, native image can work even if we give it less resources. So if I do this way, so I limit memory because, in fact, native image is quite compact and quite memory efficient, and it doesn't really need that much memory. So I can easily limit, and perhaps that is something I would be specifically interested in, let's say, in cloud environments, where memory is one of the things that I'm paying for. So I can serve a reasonable amount of requests by using so much less memory. And this is the way those two compare when you take them side by side. So that was one workload. Typically, when you make a decision whether or not to migrate to something, you may want to look at more numbers. So the numbers represented here are based on the benchmark suite called Renaissance Dev, and that is a selection of Java and Scala workloads, and the numbers you see here are in red. This is GraalVM Enterprise Edition compared to C2, and in gray it's GraalVM Community Edition, once again compared to C2. So the numbers are different, and that is why we always say, please take GraalVM and compare it on your workload, because depending on the way you write your code, depending on the dependencies you are using, the results you will get will be different. But on average, you see that you can get quite a speed up with both versions of GraalVM. Another example that I like is Scala code. How many Scala developers are in here? Okay, not a lot. So for Scala code, GraalVM is specifically good because Scala produces slightly different bytecode, and also GraalVM is specifically good at removing object allocations. So this way, it can make Scala code run faster. In this example, you see that, I'm so sorry for this, I don't know what's happening. So I will not try it. I will not touch it. So in this example, the gray one is Hotspot VM, the orange one is GraalVM Community Edition, and the red one is GraalVM Enterprise Edition. So we don't like to say like one number, but on average for Scala, you can get around 10–15% of speed up with GraalVM Community Edition, and up to 30–35% speed up with the Enterprise Edition. Talking about more frameworks, so these are a couple of frameworks supporting GraalVM native image, and this is the comparison of just-in-time compilation mode and ahead-of-time compilation mode, basically what we did with the demo. So I know that may be hard to read from the back rows, I will read it. So the first one is Helidon, Micronaut, and Quarkus, and the lines are represented in green GraalVM native image, orange is JDK 12, and red one is JDK 8. So I just encourage you to look at it as not comparing those frameworks between one another, but rather comparing those two compilation modes. So that was the startup time, and once again, in memory usage, you also get quite a difference comparing to traditional JIT setup. So a few more things about GraalVM native image. So currently, as we've discussed, it's somewhere like this on the performance chart. So you get good startup and you get good memory usage, but peak throughput and reduced max latency, this is something we are still working on. Because the idea is that we want to be somewhere like this, so remove all the trade-offs and make you be able to choose the best performance for whatever case. One more important note about GraalVM native image. So it may require some additional configuration from your side. So for things like reflection, for things like GNI and so on, you may be needed to provide us a configuration file during your image build time. So you can do this manually, and we have instruction for this, or you can use our tracing agent that will output this information for you. And if you like GraalVM native image, there are a few resources that I would encourage you to read because the scope of this talk is limited. So the first one is our reference manual, and you can find all the helpful flags in there and some additional use cases and samples. The second one is talking about improving performance of GraalVM native image with profile-guided optimizations. And the last one is from this year's Oracle Code One, our talk by the native image component lead Christian Wimmer. That's the current state and a bit of roadmap for GraalVM native image. So for the Microservice Framework support, so we've already looked at the charts for Micronaut, Helidon, and Quarkus. There are also some of the Spring apps that would work with GraalVM native image, and yesterday we've seen examples of those. If you're interested in those, you can also come to me and I will show you a bit more examples of those. Basically, you would just need to get an experimental build this project, and then you can run those sample applications. But for many applications, that would be still work in progress. One more interesting thing for GraalVM native image is the ability to optimize it even more with profile-guided optimizations. So what it means is that, as we discussed, JIT systems are able to optimize your code really well based on this profiling information that is available at runtime. And native image build is a closed world assumption, meaning that we need to know all of your code and all the information from the very beginning. So the way to handle it and also to get even better performance would be to collect profile information and provide it to us so that we can optimize your native image with this information in mind. So this is the way to do it. You basically just run your application in a test run, output this information, and feed it to native image. And what is possible to achieve if you do this, and this is the chart overviewing specifically peak throughput. These are the requests handled per second. In green here, this is GraalVM native image community edition. Red one is enterprise edition with profile guide optimizations, and the orange one, that's JDK 8 default Java hotspot VM. So you see, and like you normally would expect, right? So hotspot VM warms up over time, but then when your system reached its warmed up state, it's really good. Yeah, that's something we all know and love about Java. Then when it's warmed up, it's able to work really well. And that's what it shows. So with native image, it's slightly different. So you start with better performance, but over time, obviously, having that profile information available allows JIT mode to optimize even more. With profile guided optimizations, with this profile information that you would give to us, it is able to achieve on-par performance for both of those. So max latency. So as you know, for JIT mode, there are a couple of ways to optimize for it. There is a decent choice of GC options. For native image, it is slightly different. So currently, we only have a regular stop and copy collector. This is something we are still working on, and we expect a new GC to arrive soon. But normally, native image would kind of keep in mind small heap configurations. So just to compare those two modes side by side, GraalVM JIT is very good for peak throughput, for max latency, and doesn't need much configuration from your side. GraalVM AUT is great for startup and for memory usage, and if your packaging size is important for you. So obviously for server-side Java, this is not the most priority metric, but if you are working with devices that have limited resources, packaging size can be also relevant for you. And now for tools. So we have a thing called Ideal Graph Visualizer, IGV, and this is something that would allow you to look at the internal representation of your program graph and see how it is compiled over time and improve it. Another one that you can use to work with performance is Java flight recorder information. So it would allow you to view all of this information and see where are the performance bottlenecks and optimize against those. So, and there is also so much more that you can do with GraalVM. So the scope of this talk is performance-related questions, but there is also more capabilities. So first of all, you can build polyglot apps like this, where this is JavaScript, Java, and R all used in one application, and the result is like this, where you see JavaScript part, Java part, and this plot coming from R. There are even more fantastic projects that you can do with GraalVM. So this is the idea of building applications for various platforms, such as iOS and Android with GraalVM. And this is an ongoing project that we are doing with Gluon team. This is something quite interesting that we expect to see even more uses for this in the future. And to talk about industry use cases, so I'm sure you know this guy over here. It's Chris Tellinger. He was given a keynote today. So he is working at Twitter, and Twitter has been using GraalVM for quite a bit in production now. Twitter was one of our first early adopters. So back, I think, 2.5 years ago, they started working with GraalVM. And since they have a huge bunch of Scala microservices, this is something that GraalVM can specifically well optimized. And even with Community Edition, they are getting significant results, and those results are multiplied even more with huge scale systems like Twitter, where you have thousands of instances running, and that scale benefits even more from every single optimization you are able to do. One of the recent adopters is Oracle Cloud Infrastructure, so it's running a lot of internal services, and they migrated some of them from Java to GraalVM, and they report getting peak performance up to 10% higher, reduced GC collection times, and also what's interesting, the migration process, because sometimes we get this question like, is it hard to migrate to GraalVM? So they said no, it was fairly simple process that did not run into any issues, and it was pretty straightforward. And we also have a blog post about this use case if you're interested. And one more interested project is, this is an announcement from this year, once again, Code One. So we are working with Nvidia to make GPU kernels available from GraalVM languages, from GraalVM applications. And what is next? So this year, I did not mention this talk, but this year we published our first production-ready release, because GraalVM was a research project for about 8 years, and as of this year, we finally have our production-ready releases. So it was 90.0 in May, and since that, we had a couple of new releases. So for example, now we support GFR snapshots in Graal Visual VM. Also, we have now updated PG optimizations for native image. A few more things is LLVM toolchain that we've been talking about yesterday, and also we constantly work on new tools, such as, for example, Visual Studio Code plugin. And what's coming next? So first of all, JDK 11-based builds. This is a question we got quite a lot, like when will JDK 11 builds arrive? Though when we ask back, like what version of Java do you use, people usually say Java 8. But they constantly ask us about JDK 11 builds, and those are scheduled to arrive in the next release, 90.3, in mid-November. One more thing, we are working on new platform support. So we are working to extend our Windows support, for example. And as I mentioned, there is one more ongoing project that is new GC for native images. Also, we work with communities, so we are working, for example, to support new libraries, new languages, and new platforms, and if that is something that would be interested for you, you can also contribute to this project. A good starting point for you would be this website. If you would like to try GraalVM, this is graalvm.org. There you can get docs, samples, the actual downloads, and try it on your application. And yeah, here are a few links. I think the organizers will share those slides with you. Basically, this is where you can download it, where you can follow updates. The good source would be Twitter. And also, if you need help, we have this mailing list, and we have community Slack, where you can talk to other community members and to other team members. So I just want to summarize this talk with a few key takeaways that I would like you to take from this talk. So the first one is write small methods. This is something that a modern compiler can easily handle, and if you write small methods, you are kind of helping it, and also this is a good way to go. Also, local allocations are fairly easy to optimize, fairly easy to either remove or optimize, so local allocations would be better for your application performance. Also, please don't hand optimize, because sometimes it can be useless effort. Sometimes it can get even worse. So if you do want to hand optimize, you can take a look at the compiler graph and see what's really happening in there. And if you are like deciding between those two modes, hesitating, this is a quick suggestion. So for best throughput, you can use GraalVM JIT mode, and for best startup and footprint, you can use GraalVM IoT. That's all. That's my name. That's my Twitter handle. So if you have a question, if you want to suggest something or give feedback, please do so, and thank you.